let's look at this problem again. So I want to go from O to P, and in every step I can go 1 unit to the right or 1 unit up. And there are a bunch of forbidden edges or forbidden segments, and I don't want to cross any of the forbidden segments. So my question is, what is the number of paths from O to P that don't use any of these forbidden segments in red? Okay. We've already seen a solution using just the addition principle. We basically count the number of paths without forbidden segments to every one of the points, and we use the addition principle to compute the number for P. But now I want to do it using the principle of inclusion and exclusion. So here's the thing. I can say, consider all the paths from O to P. And then let's subtract from that all the paths that contain AB, right? Because those are definitely invalid paths. And then let's subtract the paths that have CD in them. Now, how do I find that? For example, what is the number of paths that have CD? Well, I have to find the number of paths from O to C and multiply that by the number of paths from D to P. And I know how to find those two numbers, right? So I start with all of my paths. I subtract the paths that go through AB. Then I subtract the paths that go through CD, and so on. Subtract the paths that go through EF, subtract the paths that go through GH. But now the problem is that if I have a path that goes through 2 of these segments, I have subtracted it twice, right? So for example, this path, go up, then go through AB, go through CD, and then go up, and then go to P. This path was added once, but then it was subtracted twice. So now I have to add these paths. So for any 2 of my segments, I have to add all the paths that go through both of them. So for AB and CD, I add all the paths that go through both of them. For AB and EF, I do the same thing. For AB and GH, I do the same thing. But now, if I have a path that goes through 3 of these, then I have to again subtract that. And finally, if I have a path that goes through all 4, I have to add it. But in this case, I cannot have a path that goes through all 4. Okay. So how many paths do I have from O to P that do not use any of the forbidden segments? Well, let's just do something simple. Let's say FT is the number of paths that use all the segments in T. So T is a set. Okay. So my answer would be the total number of paths minus the paths that go through AB and the paths that go through CD and so on. Basically, for every segment, I say how many paths go through this segment, and I subtract those. Plus the number of paths that go through any combination of 2 segments. So for any combination of 2 segments, for example, A, B, C, D, I have to add the number of paths that go through both AB and CD, right? Now I can go through AB and then CD. I can go through AB and then EF. So I have added this one. I can go through AB and then GH. I can go through CD and then EF, CD and then GH. But it's impossible to have any other combination of 2 of these. So I cannot, for example, have a path that goes through EF and GH. That doesn't happen. Because it doesn't happen, it's basically 0, so I don't have to add it here. Okay. And then I have to subtract the number of paths that go through the 3 combinations. So A, B, C, D, E, F. Or the paths that go through A, B, C, D, G, H. And you can check that these are the only combinations of 3 forbidden segments that are possible here. And I don't have any combination of 4 segments. So this is my final answer. My answer is the total number of paths minus the paths that go through 1 segment for every segment, minus the plus the paths that go through 2 segments, minus the paths that go through 3 segments. So this is just inclusion, exclusion, as we've seen before. And of course, I'm too lazy to compute all of these. So let's just do 2 of them randomly. So let's say ABGH. What is F of ABGH? This is the number of paths that go through both AB and GH. So I have to start my paths here, and I have to first reach A. How many ways do I have to reach A? 4 choose 2. Okay. But then I want to do AB and GH. So when I'm at A, I have to go all the way right to G. There is only one way to do that. And then from G, I have to go to P. How many ways do I have for that? 6 choose 3. So the total number is 4 choose 2 times 6 choose 3. So this one is 4 choose 2 times 6 choose 3. Okay. What about this one? F of A, B, C, D, G, H. So I have to go through A, B, I have to go through C, D, and I have to go through G, H. This is again the same as before, actually. Because I start at O, I have to go to A, and then I have to go all the way to G. That's one way. And then I go to H, and from H to O. Sorry. So in this previous one, I was doing GH. So I have to go from H to here, which is 5 choose 2, not 6 choose 3. So this is just 5. Okay. And this is, again, the same value, 4 choose 2 times 5 choose 3. So actually, these two cancel out with each other. You can find the values for all of them, and then you can do the addition, and you can see that the answer is correct. Okay. But now I can ask a more interesting question. I can ask how many paths from O to P go through exactly 2 of the forbidden segments. So in the previous session, we saw how to solve this using the addition principle as well. But can we solve it using inclusion exclusion? Do I have a way of counting exactly how many paths from O to P go through 2, not less than 2 and not more than 2, exactly 2 of the forbidden segments? So we will see that very soon. But before that, I want to give you just some more examples of using inclusion exclusion. So let's say I ask you how many prime numbers are there less than 50. Okay. Now, if this is an easy problem, you can just write a program to find it. But let's say I want to find it by hand. So here's the thing. I say if I have a number x, and this number is actually not a prime, then I can write x as a times b, where both of these a and b are different than 1 and x. So what does this mean? This means that one of these two should be more than the square root of x. Either a should be more than the square root of x, greater than or equal to the square root of x, or b, right? So if I have a number that is not a prime, I can definitely find a non-trivial factor that is less than or equal to its square root. So if I want to find the number of prime numbers less than 50, I can first try to count the composite numbers. And in order to count a composite number, it's enough if I just consider the prime factors that are less than or equal to square root of 50. So what are the prime numbers less than or equal to square root of 50? This is a much easier question, right? So I have 2, 3, 5, and 7. Every other prime number is bigger than square root of 50. Okay. So the question I have to answer is basically, how many numbers less than 50 are multiples of these 4 numbers? Okay. So I'm going to define my sets like this. I'm going to say A2 is the set of multiples of 2. Of course, multiples of 2 that are less than or equal to 50, right? Similarly, A3 is the set of multiples of 3, and so on. I have 4 sets, right? What do I want? I want to find what is A1 union, sorry, I didn't use 1. What is A2 union A3 union A5 union A7? Okay. So if I take all the numbers that are multiples of any of these 4, how many numbers do I have? Okay. Now I know how to find this, right? So this is, again, inclusion exclusion. I just have to add all the sets, all the sizes of single sets, A5, A7, and then I have to subtract intersections of 2 sets. So A2, A3, A2, A5. Basically, you get the idea. I'm too lazy to write all of them, right? And then I have to add all the intersections of 3 sets. So A2 intersection with A3 intersection with A5, and so on. And I also add all the other ones. And then I have to subtract the intersection of 4. A2, A3, A5, A7. Okay. And again, for each of these terms, you know how to find the number. So for example, if I look here, these are numbers that are multiples of both 2 and 3. So they're the numbers that are multiples of 6. How many numbers do I have that are multiples of 6? 50 over 6. And of course, the floor of this, right? So I can find each one of these numbers. Again, I'm too lazy to do it, but you can do it, hopefully. So this will give you the number of elements in that set, in that union. So let's call this something. Let's give it a name. Let's call this L. Okay. So I can find this number L. But what is L? L is the number of numbers between 1 and 50 that are multiples of 2, 3, 5, or 7. Right? But I want the prime numbers. So I have to just take 50 minus L. So I remove the multiples, but I have to still do some adjustments. So 2, 3, 5, and 7 are themselves counted here, right? So plus 4. There is also a minus 1 at the end. Yes, because 1 is not a prime number, right? So this is my answer. Okay, now, honestly, do you think this is easier than going over each of the 50 numbers and seeing if they're prime or not? It's up to you. I'm just giving you one way of doing this. And again, as a computer scientist, I pretty much hate any algorithm that is based on inclusion exclusion. Because look, if I have n sets, I have to look at 2 to the power of n different terms here, right? So unless I have a way of grouping these terms and finding the values with fewer computations, I'm not going to use inclusion exclusion in any algorithm. But again, this is a mathematics course, so you can find it like that. Okay, let's see another problem. And this is very similar to the problems we've seen already, but I'm going to add, I'm going to add a harder condition here. So again, we have the same linear equation, x1 plus x2 plus x3 equal to 10. I want to see how many integer solutions I have. But now, other than lower bounds, I also have upper bounds on my variables. Okay. So previously, if I didn't have these red upper bounds, I know how to solve this, right? But now I have upper bounds. So I say that x1 should be at most 5. You cannot assign more than 5 to x1. x2 should be at most 8. And x3 should be at most 7. Okay. How would you solve this? Again, I want to define a bunch of sets, and then I want to be able to use inclusion exclusion. Okay. So I can first ignore all these red upper bounds and find the total number of solutions. I know how to find that if I didn't have these upper bounds. But my answer would be the total number of solutions minus the number of solutions that violate the first upper bound, minus the number of solutions that violate the second upper bound, minus the number of solutions that violate the third upper bound. But now if I had a solution that violated 2 of them, I have subtracted it twice. So plus the number of solutions that violate these 2, plus the number of solutions that violate these 2, plus the number of solutions that violate this one and this one. And finally, minus the number of solutions that violate all 3. Okay, so that's what I want to find. Okay, so basically this is what I'm saying. I'm saying, imagine that A1 is the solutions, it's the set of solutions to this, let's call it star, that violate the first condition, that violates x1 less than or equal to 5. Okay. And then I say A2 is the set of solutions that violate the second condition, x2 less than or equal to 8. And A3 is the set of solutions that violate x3 less than or equal to 7. Okay. Now, what do I want? I want to know what is the size of the union of A1, A2, and A3, because these will be all the solutions that violate at least one of my constraints, and then I can subtract that from the total number of solutions, and that gives me the answer. So my answer is the total number of solutions if I didn't have these upper bounds. What is the total number of solutions if I don't have these upper bounds? So I have 10 balls and 2 valves. It's 12 choose 10. Right, 12 choose 10 minus the size of A1 union A2 union A3. Okay. But now I know how to find this size. I know that if I have A1 union A2 union A3, the size is actually just the size of A1 plus the size of A2 plus the size of A3 minus the size of A1 intersect A2 minus A1 A3 minus A2 A3, and finally plus A1 intersect A2 intersect A3. So now I have to go and find each one of these 7 terms. As usual, because I'm very lazy, I'm going to just do some of them. So first of all, this last one, A1 intersect A2 intersect A3. What does this mean? It's violating this upper bound, so x1 is at least 6. It's violating this one, so x2 is at least 9. And it's violating this one, so x3 is at least 8. There are no solutions. There are no x1, x2, x3 that sum up to 10 if I have those bounds. So I can be pretty sure that this one is 0. Okay. Now, but let's just look at one of these. Let's look at A1, for example. So A1 is the solutions, the set of solutions that violate this first upper bound. So what does it mean? It means that I basically have the same thing. So when I want to find A1, I have the same equation, x1 plus x2 plus x3 equals 10. But now I know that this bound is violated. So x1 is at least 6. Okay, so 6 less than or equal to x1. But x2 and x3 are greater than or equal to 0. I want to see how many solutions I have here. And the number of solutions to this system is going to give me the size of A1. Okay, now how do I do this? I just define a y1, which is x1 minus 6, right? And then I have y1 plus x2 plus x3 equals 4. And all of these variables should be greater than or equal to 0. So in this case, I have 4 balls and 2 balls. So the size of A1 is 6 choose 2. Okay. So again, you can find all of these things one by one, and then you can compute this whole thing. And of course, our answer is the total number of solutions minus this size. Great. But now we want to see a generalized version of the principle of inclusion exclusion. And this is based on this small question that I had written here. So look, I have 3 bounds. And so far, I asked you how many solutions satisfy all 3 of these bounds of the red upper bounds, right? And I gave you the answer like this. But what if I say I want you to count the solutions that satisfy exactly 2 of these 3 upper bounds? Can you answer that? You should be able to answer it immediately. 0. Yes. Because if Oh, no. I didn't say that violates 2 of 3. I said that satisfy 2 of 3. Okay, no, not 0. Right? So like 2, 2, 6 is a solution. No, but it doesn't violate this one. Okay, 1, 1, 8 is a solution that satisfies exactly 2. Right? Okay. If I want the number of solutions that satisfy exactly 2, I can do a casework. I can say which 2, right? And then I can just find the number of solutions that satisfy the first 2. Then I can find the number of solutions that satisfy these 2, and so on. But I have to still do inclusion exclusion, because there might be some solutions that satisfy 2 different pairs, right? So this is a bit hard. Can I do a better argument here? So here's the thing. If I have a solution, it's going to satisfy either exactly one of these equations, or exactly 2 of them, or all 3, or none of them. So I can just do a casework and try to count each one separately. Okay. Now, I want to give you a way of doing this casework, but more systematically. So this is what we call generalized principle of inclusion exclusion. And the reason that it's not generalized inclusion exclusion principle is that we still want to have pi there. Okay, so the situation is similar as before. Let's say that I have a big set. So I have a universe set with n elements. So for example, in the previous case, my universe was the set of all solutions to these equations where I didn't consider the upper bounds. That was my universe, right? And then let's say that I have a bunch of subsets in this universe. So let me make sure that I'm using the same notation as the book. Yes. So let's say that I have A1, A2 to AQ, and these are just sets. Okay. Now, we defined something before, and that was omega m. So I said that omega m is just the sum of the sizes of the intersection of m of my sets. Okay. So I take any possible combination of m of my sets. I take their intersection, look at its size, and I add up all these sizes. And I said, I show that with omega of m. Okay, this was what we had in the last session, basically to avoid writing this sum over and over again, because I hate writing this sum. Okay, so here's what I want to say. I want to say that if I look at every element, it either appears in none of my sets, or exactly one of my sets, or exactly 2 of my sets, so on, or exactly q of my sets. Okay. So here's what I want to say. I want to define something called exactly m, or em. And this is going to be the number of elements that appear in exactly m of these sets. Okay, so the number of elements appearing in exactly m of my sets. Okay, I want to find a formula for this em, because if I find that, then I can answer questions like this. I can say how many solutions satisfy exactly 2 of the red bounds, or I can answer a question like this one. I can say how many of the paths from O to P go through exactly 3 of these segments, right? So I want to answer exactly m questions. Okay, how do I find this? How do I find the number of items that are in exactly m of my sets? Now, the book just gives you a formula and then proves it. But I want to give you some intuition for where this formula came from. So let's say I want EM. So I want to count all the elements that appeared in exactly M of the sets. Okay. So the first thing I say is I say add omega M. What is omega M? It's basically saying look at all the combinations of M sets, look at all of their intersections, and count any elements that is in those intersections. Okay. Now, if I have an element that appears in less than M sets, I have not counted it here because this one only counts the intersections of M sets. Okay. If I have an element that appears in exactly M sets, I have counted it once because, again, it considers all the combinations of M sets. And if I have an element that was only in M sets, then there is only one combination that counts it. But my problem is with the elements that appear in more than M sets. So let's say I have some element X, and let's say that this X appears in M+1 sets. Okay. I want to see how many times it should be counted. So on the left-hand side, it should be counted 0 times because this is supposed to be the number of elements that appear in exactly M sets, and X is appearing in M+1 sets. But is it counted on the right-hand side right now? Yes, because if X appears in M+1 sets, then whenever the M sets that I'm using here in this combination all contain X, I'm going to add X, right? So how many times have I counted X? How many times? M+1 times. Or to be more specific, M+1 choose M. Because again, imagine it like this. I have this X, and I have M+1 sets that include X, right? So let's say my M is 2 here. So I have 3 sets that include X, right? But here I'm considering any combination of 2 sets. Okay, and I'm adding the size of their intersection. So for any 2 of these sets, X was counted once here, right? So overall, X was counted 3 choose 2 times. Or if instead of M+1, instead of 3, I just say M+1, X was counted M+1 choose M times, right? But I don't want that. I want X to be counted 0 times. So I can just subtract it, right? So let's say I subtract M+1 choose M times omega of M+1. Okay. So what was omega of M+1? It was that I take all combinations of M+1 sets, look at their intersection, the size of the intersection, and so on. And of course, I want to subtract that because in this, X is counted exactly once, right? But in this one, X was counted M+1 choose M times. So I want to subtract this to make sure X is not counted. Okay. Is everyone fine until this point? So right now, on my left side, again, EM counts only the elements that appear in exactly M of my sets. On the right-hand side, so far, I've made sure that I don't count any element that appears in less than M sets. I've made sure that if I have an element that appears in exactly M sets, I count it once here. And I've made sure that if I have an element that appears in exactly M+1 sets, I haven't counted it because I add it here, M+1 choose M times, and then I subtract it, M+1 choose M times. Okay. You see where this is going. So the next case is this. Let's say I now have some element X that appears in M+2 sets, in exactly M+2 of my sets. Okay. On the left-hand side, I'm not counting X. So I have to make sure that I fix the right-hand side so that it doesn't count X. So how many times is X counted on the right-hand side? So in this first one, it's counted m plus 2 choose m times, right? Because again, this was the sum of the sizes of all the combinations of m sets, intersections of combinations of m sets. And if x appears in m plus 2 sets, it appears in these many of the numbers in this sum. Okay. Minus, well, of course, I have this m plus 1 choose m from here. But how many times is x counted in this one, in omega of m plus 1? M plus 2 choose m plus 1. Okay. So right now, this is the number of times that I'm counting x on the right side. But I want to count x 0 times. Okay. So I want to basically subtract this times Wm. But what is this? What is this value? Can we simplify this value? Any ideas on how to simplify it? So here's one example. What is this? So let's look at this. Let's say that I have a class of m plus 2 people, and I want to choose m plus 1 of them, right? And then inside this m plus 1 chosen people, I want to choose another m of them. So I want to create 2 teams, but I want one team to be a subset of the other one. So I first have m plus 2 people. I'm choosing a team of m plus 1. And then inside this team of m plus 1, I'm choosing a team of size m. This part is the number of ways of doing that. But another equivalent way of doing the same thing is that I have m plus 2 people. I first choose m of them for the second team. And then I have 2 people remaining. I have to choose one of them for the first team. So instead of this, I can just write m plus 2 choose m times 2 choose 1. Right? And 2 choose 1 is just 2. So 2. And here I had m plus 2 choose m. So interesting. The number of times that I've counted x on the right-hand side is m plus 2 choose m minus twice the same number. So actually, I've counted it a negative number of times, right? So I have to add it back. I have to make sure I count it 0 times. So I have to add m plus 2 choose m times of that. So I have to update my right-hand side and say plus m plus 2 choose m times omega of m plus 2. Okay, is everyone fine with this one? Okay, next step. Let's say that x appears in m plus 3 sets. Okay, how many times is it counted on the right-hand side? On the left, I've counted it 0 times. On the right, it's counted, if I look at this one, m plus 3 choose m minus m plus 1 choose m times m plus 3 choose m plus 1 plus m plus 2 choose m times m plus 3 choose m plus 2. Okay, this is the number of times that it's counted. But I want to make sure that it's counted 0 times. So I have to subtract this. Now, very similar to the case before, you can actually prove that this is minus m plus 3 choose m. Okay, just apply the same arguments as before. So basically, this is what I'm going to have. Let me delete all of this because this is now a longer formula. I'm going to have minus m plus 3 choose m omega of m plus 3. Okay, And it just continues like that. So plus m plus 4 choose m, omega of m plus 4, and so on. So if I want to just write it in a simpler way, E of m is going to be the sum of k from m to q. And remember, q was my total number of sets, so I have q sets. Minus 1 to the power of k minus m, k choose m, omega k. Great. So how do we prove that this is correct? I gave you the intuition. You can read the proof in the book. Basically, you say that for every element x of my universe that I take it, it's either appearing in exactly one set or two sets or three sets or so on. And you just do a casework. And in every case, it's counted 0 times on both sides, except when x appears in exactly m of the sets, in which case it's counted exactly once on both sides. So we have this equality. Okay. Now, what does this mean for this problem? So let's say that I want to find the number of ways that go through exactly 3 of the forbidden segments here. Okay. So how many ways, how many paths from O to P go through exactly 3 of these? Okay. So coming back here, let me just copy my formula. Oops, too much. This is next session. Okay. Let me copy this formula. So this was my formula. And here I want to put the formula. And I want to say, well, my M is 3, right? So M is 3. So basically, I want to say how many of the paths go through exactly 3 of these forbidden segments. Okay. So what can I say? I can say E3, which is the paths that are in the intersection of exactly 3 of my sets, is going to be the sum of k from 3 to 4, because I had 4 overall, minus 1 to the power of k minus m, k choose m, oh, m was 3, k choose 3, wk. So basically, what is this saying? This is saying that first, I look at W3. What is W3? It's the sum of the sizes of all the intersections of 3 of my sets, right? And from that, I have to subtract what? I have to subtract 4 choose 3, W4. Because if I have a path that goes through all 4 of my segments, it's counted 4 times here, but I want to count it 0 times. So I have to subtract it 4 times. 4 choose 3 is 4. Right? Now, in this case, again, I'm lucky W of 4 is 0. Because I don't have any paths that go through all 4 of these segments. Okay? So I just have to find W of 3. And W of 3 is basically, I have to look at every subset of 3 paths out of these 4, 3 segments out of these 4, and I have to ask how many paths do I have that go through all 3? But it's this thing that I have here, right? Of course, not negative, but positive. Okay, so I don't have the minus there. Okay, because these were the only possible combinations of 3 segments that I could have in my path. And for each one of them, I'm counting how many paths go through. And again, we've seen how to compute these things. Okay. So I can find out exactly how many paths exist that go through exactly 3 of these segments. But here's the thing. Doing inclusion exclusion was kind of overkill here, if you think about it. Because look, if I want to go through 3 of these segments, I can just look at this and I can already know that, well, it's either going to be A, B, C, D, and E, F, or it's going to be A, B, C, D, and G, H. And these are 2 completely separate cases. So I can just do case fork, principle of addition, add the 2 cases. But inclusion exclusion works for any combination of these, of course. So if my forbidden edges were any different, I wouldn't be able to just do a case fork, but I would still be able to do inclusion exclusion. Okay. So here's another interesting problem. So we've talked about derangements. Derangements, we said, are permutations of the numbers from 1 to n, where no number is in its own position. So let's say that I call a number that is in its own position a fixed point. So if I have a permutation p, a fixed point of p is just some index I, where the value at index I is equal to I itself. Okay. Now I want to say I have n elements. So I have this set. Again, remember, this is 1, 2 to n. But I want to create an R permutation. So I want to take only R of the elements and put them in some order, in some queue, right? But additionally, I want to make sure that I have exactly k fixed points. So I have exactly k indices where the number is equal to the value. Or another way of saying this is that I have n people numbered from 1 to n. I have R chairs numbered from 1 to R. I want to choose n of these people and put them on the chairs so that for exactly k of the chairs, the number of the chair and the number of the person is the same. Okay, that's what I want to find. Okay, how would you say I can do this? So first of all, what is my universe here? I would say that my universe is all the ways of putting R people on the R chairs. Okay, so the size of my universe is just going to be P of NR. Because remember, this was the number of ways of creating a permutation of R people out of N people. Okay, that's the size of my universe. But now what are the sets that I want to look at? So let's say A1 is the set of R permutations where 1 is a fixed point. Okay, so I say A1 is the set of all permutations P such that P1 is 1. Okay, and similarly, A2 is going to be the set of all permutations where P2 is 2, and so on. And I'm going to continue this until AR. AR is the set of all permutations such that the R's position of the permutation is R. Okay. What do I want? I want the number of elements or the number of permutations that are in exactly k of these R sets. Okay. Or using my notation from before, I want E of k. Okay. How do I find that? Actually, I just realized that I used to use M before, so let me just change this. Let's say M fixed points, because that's what I used in the previous problems, right? So exactly M fixed points, and I want E of M. I want to know how many elements are exactly in M of the sets. Okay. Now, again, I have this same formula as before, which I just proved. So I put it here. This is what I want to calculate. Okay. Let's see. Basically, I need to find these omega values, right? Because if I find the omega values, I can just plug them in here and I have my answer. So what is omega of k? Remember, omega of k was by definition the sum of all the intersections of k elements, right? Now, am I not lucky? All of these intersections have the same size in this case, right? So let's say that I want to find the intersection of AI1, AI2 to AIK. What does that mean? That means that I want to find all the permutations where I1 is in position I1, I2 is in position I2, so on, to IK is in position IK, okay? So I have K people who have to go and take the seat that has the same number as them. And now I want to create the rest of the permutation, okay? So I want to find this. And basically, the situation is this. I have R chairs, but K of them are already filled. So the indices I1 to IK, I know that the person with the same number as the index should go and sit there. Okay, so how many available chairs do I have? I have R minus K chairs remaining, right? How many available people do I have? Well, K people have already taken a seat. So I have N minus K people. So I have N minus K people, and I want to create a permutation of R minus K of them. So the total number of ways of doing that is just P of N minus K, R minus K, which we've seen is the same as N minus K choose R minus K times R minus K factorial. Okay. So now what do I know about WK? WK is the sum over all possible I1 to IK, but then the thing that I'm summing up is always this same value. So I just have to figure out how many different combinations of I1 to IK I can have, right? Because this is a sum that is going over all the possible combinations of I1 to IK, and in each iteration, it's just adding this value, okay? So how many combinations of IY to IK can I have? Yeah, I have R sets. I want to choose K of them, so it's just R choose K. So this whole thing is equal to R choose K times P of N minus K, R minus K. And finally, I can just plug everything in, right? So I can say that the number of elements that are in exactly M sets, which is basically the number of R permutations of this set that have exactly M fixed points, is just the sum of K from M to R, right? Because this Q is actually R. I have R sets here. Just R here. And then this thing, -1 to the power of K minus M. And K choose M, omega K. So K choose M, and then omega K was this one. R choose K, and then this one, P N minus K, R minus K. Okay, this is my answer. Now, honestly, you can really simplify this. You can just write out all of these things. You have a lot of factorials that simplify, so you can get a more simplified answer than this. But I could count this using the inclusion-exclusion principle, right? Let's give this a name. Let's call this answer, which was E of M, let's call it the number of derangements with N elements. I'm choosing R elements, and I have M fixed points. Okay. So what is the number of derangements that we had on N elements before, the first thing that we counted? This would be the same as the case where I put R equal to N and M equal to 0. So now I have a more general case of the same problem that I solved before. Not only can I count the number of derangements, the number of permutations where no one is in their own position, but also for any given M, I can find the number of permutations where exactly M people are in their own position.